Yeah. Thank you, everyone. My name is Erica. I'm currently a PhD at Stanford, also a research fellow at Jump Trading. Previously, I worked as an applied scientist at Amazon, working on kind of the similar topic that I'm going to present today. So today, I kind of want to focus on the evaluation side of things. Thinking about like what happens if we don't have a very clean verifier domains like math or code. What if we go into more fuzzy domains that are not very cleanly verifiable, such as negotiation, a lot of the social tasks, marketplace, a lot of those behaviors, social behavioral tasks? What happens if we want to evaluate agents in those spaces when clean verifier story no longer is there? And today I'm going to kind of focus on a very new work that we just released, and it's called Terms Bench. It is a case study of like how we can build verifier when there are no there's not a very clean kind of a straightforward solution to it, and how we can kind of create evaluation for semi-verifiable domains when the story breaks down. And we're going to focus that on negotiation agents in particular. This is a joint work with HAI and Stanford Engineering, as well as Stanford Economics and Stanford School of Business. And these are kind of the authors, and we're happy to present it tonight. So a little bit about the motivation of like why we do this. In agentic evaluation, we can roughly kind of like separate it into three categories of like verifier spaces. The first is obviously verifiable domains like math, code, and these has been like sort of like the story behind a lot of like progress we've seen recently in agentic spaces like cloud code agents. We see a lot of like that's sort of like the clean verifier evaluation benchmarks are behind a lot of the progress that we've seen lately driving these agents forward. And in the middle, we have semi-verifiable domains. These are like multi-turn sort of interactions, social interactions, like communication judgment, strategic reasoning. The outcomes are usually verifiable, like you can tell if an agent wins something or not, and you can often tell like how much it makes on the marketplace. But the process of how it gets there is usually very elusive. There's not a clean way of like how to understand how an agent get to that place and how to evaluate if an agent does well or bad on that. And that's what we call semi-verifiable domains. And on the other end of the spectrum, we have like non-verifiable domains, and these are like up to a lot of creative judgments that we can a lot of creative tasks and open generation. So recently we've seen a lot of like improvements in coding agents, and the story is like it is currently a lot harder to find coding tasks that agents are going to fail on than it was a year ago. So agentic capabilities are scaling really, really fast on a clean verifiable sort of domains. So the headroom is kind of shrinking fast. But the story of how to evaluate agents in like lesser available verifier available spaces like semi-verifiable domains are still like currently very underdeveloped. And so this work that we're kind of looking at it from a very structural way and from a methodological perspective of how we can make it rigorous and how we can sort of like really understand agentic capabilities in this domain to enable to help to scale the agents in the next sort of intelligence spaces, which I believe is going to be a very important step for the next step of agentic intelligence, and that's in these type of social spaces. Sorry, a little bit more. And like where the stakes are highest, and another motivation of like why we do this and why we focus on negotiation in particular is that these are usually domains, like social domains, that have a lot of like high stakes because it's marketplace negotiation, and you're like usually the agent is communicating with the customer directly. So there's a lot of high degree of requirement for like safety, and the stakes are really high. So there's a very big demand on like how we do it like rigorously methodologically, knowing where agents fail and succeed before it gets deployed. And that's sort of like the task that I've been thinking about when I was building the negotiation agent as an applied scientist at Amazon last summer. It's like how we can like build an agent that is observable like to the deployer, and then to make it safe before it gets deployed to the market, because just $1 kind of like an error that it makes on the market translates into $1 billion of loss if you kind of deploy into a billion sort of deals. And that is that is kind of like the story that I want to focus on, is how do we sort of reconstruct those verifier back, and how can we build better agents by having a better evaluation methodology. So the approach that we took is sort of a very, very new approach that currently should be the first to do in semi-verifiable domains. So a little bit background on like what the academic landscape is currently on evaluation for semi-verifiable domains. We have like basically two like big schools of method of evaluation. The first one is LLM as a judge. This is a very commonly used sort of a technique when you don't have a clean verifier story. And the second one is a sort of an outcome rule matrix that you sort of like compose everything into a final outcome rule, and then you decide if an agent does well or does it do like bad on that simple single outcome rule. But very big drawbacks on like either of these two approaches is that it doesn't tell you like exactly where agents fail, like why does it fail, where does it break down, like in the process. There is no kind of transparency into what is happening through the process, because the kind of the judge or whatever evaluator that you're using at the end is something that is a black box, like an LLM, and something that we don't have like an understanding to. So you can't really have transparency into how exactly is your agent performing. And we kind of reconstruct the story by, instead of like relying on a black box as a judge, we kind of reconstruct the environment from ground up. And we choose negotiation as a very like a good first step, because this is a entity that's been studied very well in economics. It's been studied very well in economics since like 1980s. There are a lot. It's basically a form of extensive form incomplete information game. It's a Bayesian incomplete information game with extensive form, and that kind of like, because it's been very structurally and rigorously studied in economics, and we actually have Stanford economics professor working on this with us together. So it gives us a very clean test bed to sort of construct a simulator for it, where we kind of like can parameterize the environment. It's sort of like building, it's like, oh, you're building a simulator for a robot. We're building a simulator for agents in semi-verifiable domains, and have it like to be a very reasonable, like sufficient statistics sort of a description of these domains by building the verifier by using environment as a verifier. And that is kind of the third path that we're proposing. And the paper is kind of technical in how we reconstruct the Bayesian-game environments. But basically, we have a formal specification that is grounded in the whole economic theory of like this bargaining environments, the minimum sufficient statistics to describe this sort of task. And then we have like a counterpart in which we construct as an opponent in this arena. It is sort of parameterized as a stochastic kernel. It has its policy is like fully transparent to the evaluator, so we can like tune it to be whatever characteristics we want it to emulate in the actual marketplace. We can make it an adversarial opponent and any like sort of a behavior that we want to emulate in the marketplace. Because it is a stochastic kernel, we can sort of control and tune it in a way that we kind of want it to behave, to stress test our agents on specific capability axis that we want to stress test it on. And third is we do not rely on LLM as a judge or like any sort of a black box outcome matrix. And we instead use like programmatic diagnosis along several important axes of like how we evaluate humans as like a good negotiator. And these like are like roughly like 4 axes, like terminal value, agreement calibration, opponent modeling, how good it is to like the agent to sort of inference the opponent behavior to do strategic reaction to it, and protocol compliance, which is important for like business deployment. Like, does it comply with your constraints? Does the agent like how robust it is? So basically, the clean version is that we're basically constructing environment itself as a verifier. And this is the third approach that we're taking to these sort of tasks that hasn't been existed before. A little bit more on the testbed design. This is like a very rough sketch, but we consider like regimes and also counterpart families, which is like kind of the opponent that we want to construct. The regimes are like basically the 3 regimes that are very classical in like negotiation. You have like overlap, where like your zone of agreement, zone of possible agreement, your reservation value and the seller's reservation value, like you actually have a deal to make basically. And then there's also asymmetric urgency, like what if one party is more urgent than the other, like one party needs to fulfill the deal, like in a more like urgency than the other parties, like what happens in that domain. And thirdly, it's like no deal domain. There's not an agreement to be reached. Can the agent detect that instead of like breaching its own constraint to make the deal happen where the deal should not have happened? So that's kind of a stress test domain to see like agentic compliance, and also it's like intelligence in recognizing there's not a deal to be reached and can walk away from infeasible deals when it can. And then the counterpart families, we kind of decompose it into two axes, which is our core family axis. The first axis is along like how like type driven it is. So type driven, you can think about it like we communicate or like we talk in the market. A lot of people, when they negotiate, they're very personality driven. So a lot of their strategy comes from their personality. If they're an amiable person, they probably are more conciliatory. But on the other axis, they're more strategic. So like they're not entirely personality driven. They're more like strategic about like what the opponent does, and it reacts in that way. And the second axis we compose is kind of like Q axis, like how expressive is the kind of counterpart surfacing its cues, like sentiments, like its behavior, conciliatory, in its linguistic surface. So that's how we compose it into like candid, strategic, expressive, and taciturn along those four axes. And in addition, we added two stress tests. One is adversarial and the other is stochastic. Adversarial counterpart is designed to be maximally like maximally like adversarial opponents. It uses a lot of hardball behaviors that we kind of stress test the agent of like how it can keep up its like strategic sort of game in those stress test setting. We also have stochastic, that's kind of like a bad faith negotiator, like it has very noisy prices and queues, and see if agent can act robustly with those two. So a little bit of story of why we build a verifier. This is a little technical, so I'm just gonna brush through it very quickly. But because everything is like parameterized, we can actually compute a base optimal reference policy through dynamic programming to see like what is the theoretical optimal gap that we can have like on the specific parameterization and like opponents, and evaluate and kind of introduce a lot of intervention experiments that people usually do in causal inference and economics all the time into agentic evaluation, and see where exactly the bottlenecks for each agent is in these sort of tasks. And that is a very big gain that we can have with these sort of approach that is not available to you if you use the black box or like outcome rule metrics as sort of like the tool, which is kind of the landscape currently. And one of the sort of intervention that we look at is like how good is the agent at metabolizing information into actually strategic gain. And that is what we call the Oracle gap decomposition. We kind of decompose it into inference quality, uncertainty quality, and control quality of how it's able to act in along those three domains. Just to brush through really quickly, like all of these are like with respect to the base optimal policy that we can compute based on this environment via DP. But you can see that like each agents that we tested on, like Opus 4.7, GPT-4o Mini 4.6, and Grok 4.2, they have a distinct profile into like where the structural bottleneck is in sort of these type of tasks. And you can see that the composition is not quite the same across the agents, and like they are facing different structural bottlenecks. So GPT-4o Mini is the sub-frontier reference that we include specifically and purposefully for this task to see how it compares with like more frontier models like Opus 4.6. And you can see that 4.4o Mini is mostly control limited. And what that means is that it has a very poor ability of metabolizing accurate information into actual strategy. And that is like where its gap is coming from. It has problem in planning its actions by using information in a correct way. And Cloud Opus 4.6 seems to have like the gap relatively like decomposed across these three axes, with mostly like uncertainty limited. That means that there's still remaining kind of like planning error that it needs to solve with like sufficient amount of information. So the better the frontier models are, like the less that they are relying on sort of like the control as a main failure bottlenecks, but structural bottlenecks still exist for these models. And each of them kind of have a different bargaining fingerprint profile, etc. So I wish I could do the leaderboard demo, but it's the website here. We evaluate the best models currently from each like providers out there, and because we want to give everyone the best shot that they have. So we use extra high reasoning effort for all of them. So it should be like the best performance that each provider has to provide. And one interesting thing is like two interesting things I will like mention like briefly. One is that the capability like ranking does not really match one-on-one to like what you see on these models performance on verifier clean domains like Sweetbench or like a lot of like these coding bench. And that means like the capabilities that models do have in a lot of these verifier clean like one-step solution doesn't necessarily translate into a strategic social action. They are like not exactly orthogonal, I would say, but they are quite distinct. And so it's very interesting to see like how agentic capability do have a gap when it transfers like kind of capability from like one domain to the other. And second, I want to mention is that right now it's like a lot harder to get models to do to fail on coding tasks, but the headroom for like models to fail on hard strategic tasks is still very big. So in our like hardest setting, which we can make it even harder, the best model only have like Cloud Opus 4.7 extra high reasoning effort only achieves 50% of what Oracle policy can achieve. So there's a lot of headroom for like how models can improve there. And the environment that we set up is purposefully like relatively simple to like optimize for like interpretability. So there is still a big gap into like optimizing agentic performance on these type of tasks. It's far from being saturated. So just to like sum everything up, of like another kind of like gain that you have by using the third path, which is constructing environment as a verifier, is that now we can use these constructive verifiers as RL signal and to train better agents using that. Not only do we know like have attributable diagnosis of like where agents fail in this process, but we can also have like a constructed testbed that you can use these verifiers as like RL signals to train better agents on these domains. And yeah, like the third point is just the structural headroom that I mentioned. There is a heat map in our leaderboard website, which kind of shows you like how agent performance are still has like a gap to hit as you scale the difficulty up. And all of these do not require humans sort of in the process or like LLMs judgment. A lot of these we build these like environment from scratch is so that we want to create a versatile tools for practitioners to sort of tweak the environment, like tune the parameters and variables in order to kind of like test their agents in whatever specific capabilities they want to test on and make it however hard they want to make it in specific field to kind of tailor it to their own domains. And that's also another kind of a pro of like having this sort of a verifier as environment as a verifier approach is that you get to actually customize the environment in order to customize it for the specific agentic capabilities that you want to emphasize on. And in our little leaderboard, we also like provide like 3 scenarios, and one of 2 are commercial extension. One is a stateful agentic procurement chain. Like what if you give agents memory and have it negotiate with suppliers over a long horizon, like how much does it make and does it go to ruin, right? Like each procurement like settings have like a price to pay that you want to like be able to like extract more benefits than the cost you pay to like enact those procurement settings. And we see that weaker models like GPT-4o mini goes to ruin, like Grok 4.2 also is hovering around the ruin axis, while stronger models like Cloud Opus 4.6 and GLM 5.5 are doing well on these axes. So that's like kind of a simulator for like real world domain. And secondly, is we also like are kind of like anchoring these prices into like actual price catalog data from Amazon history price, which people scraped from like camel.com and see like if that does transfer there as well. And then we have we've seen that like stronger models usually perform with like real world like price geometry, which is a very big variation and fluctuation than the synthetic ones, while weaker models does worse on that. So it's also an interesting thing to see, but like as I mentioned, because it's parameterizable, so there's a lot of customization out there that's possible for each like need of front practitioners. Yes, and that is like all I'm going to present today. Happy to take questions. Yes.
So my question is about first of all, dimensionality. Actually, I don't even know if there's a good answer to. I want to hear your opinion. So this is fantastic if you can take a derivative of all the verticals and put it on a single scalar, right? Or we can objective look at the cost function. I wonder what happens. Like I'm assuming most of the negotiations are one-offs, right? How do you verify? Say we want open straight performance. We also don't want a nuclear strike. We also do not want troops on the ground. We need a hand messenger, right? And then how do we build a verifier for this unique situation where like what would it even train on to be able to read from the other side what to negotiate, how to get the signals, what their urgency is, and so on. It seems to be like the number of dimensions on the domain is so big that's like ultimately this whatever we train would be. But maybe I'm wrong, but it would be subhuman when it comes to a good negotiator. Am I wrong? Like
Yeah,
like
yeah.
non-verifiable domains are too hard.
Yeah, I think that's why we focus on semi-verifiable domain, where like there is a structure to it, like in the bottom. Like, well, I think what you're getting at is that a lot of the real world negotiation tasks are highly contextual, right? Like, it will be completely different if you're like negotiating with a logistics supplier to negotiating with like an insurance provider. And I think that's real. So the kind of that's why like I think a specific kind of like capability or like like specific evaluation of agentic capability in those like has to be customized to that specific context. What we're doing here is that we're building the minimum sufficient statistics to describe the task, right? All of these specific contextual domains that you're describing share a interface. They requires agentic like reasoning on their multi-steps. They require you to accurately inference the opponent's motives. Well, each of these specific contextual application of it has a different weight on like how important that specific capability access is, but they all share sort of like a shared structure to it. And what we're wanting to do here is that like to build a minimal sufficient statistics description of this like domain that evaluates agentic capabilities that do transfer into like more contextual and more specified domains. Yeah.
So you have a mini version of this, and you have a Bayesian approach, right? Where the information of the other side is unknown.
Yeah, it's incomplete information.
Yeah, so that there is a tiny version of this problem in your space, too, right? Like you don't know how urgent it is for them, or whatever they say is true, or how much they're willing to go down to. So so how do you deal with that in your space?
We parameterize it. There's a thing called latent type, which I kind of brushed through it because it is too deep in the details. But latent types basically we kind of parameterize, like this is also in like economics theory. Like each person has like a latent type, which is reservation value that is unknown to the other party. Your urgency, it is also unknown to the other party. Your personality, like a positive, like negative, neutral, it's also unknown to the other party. Your outside option, that is also unknown to the other party. You can parameterize these, like for a specific contextual, like in logistics, maybe you want to add any like other things, then you can add the variables back to the environment and to evaluate it. So there's a kind of a very versatile framework that economists have built for these type of things. And it's the incomplete information extensive form game. But obviously, like if you want to test like how it translates into like a one-on-one mapping thing, like that's kind of the next step we want to see is also like do human studies on it and see like how well like models correlate in the ability transfer. But yeah, thank you.
Please, clarify question based on what you were just talking about. So if I'm understanding this correctly, is the ecological validity of your verifier is defined by your friars, and then your friars are, I guess, modeled by semikinetic game theory. Is that correct?
Yes. It's sort of a minimal statistics you can think of. It's sort of like the world of Plato. Like you have like this perfect world that a lot of things like share. You know, it's like a superset. But you can instantiate it into specific different variations of it. Yeah.
Is it quick follow a candy game this time? So if I know
game.
the economic theory has a specific set of like personalities, let's say personas, then I pretend to fit into one to get in so that I can take advantage of the AIs.
One thing like interesting finding that that we do find, I'll go to you later, is that like a lot of the agents, right, like Cloud Opus 4.6, like GPT models, they have very stable bargaining fingerprints. They have a very stable pattern over like how they negotiate. So like an interesting thing is like, can you build a maximally adversarial opponent customized to the model's profile. That's also very interesting. What we found out is that the fingerprint is quite stable across a lot of the domains. Yeah.
So on the practical application side, what would you see as in timeline for initial adoption beyond piloting, testing, etc.?
Practical timeline. So I think so for this, it's right now it's like very new. We are basically the first one to build the environment from scratch. So we just released this paper like a week ago, and we presented at the Google DeepMind Gemma event. Actually, the Gemini suite model does really well on these social strategic tasks, by the way. Yeah. But there's also going to RL. Next step, right? Like making the environment more versatile, do the human studies, like see how much it transfer, and then you can try to like scale better agents on these and see if you can actually have a performance gains. So I think it's advancing very quickly. Like we have people that are ready to build, and hopefully we'll like see the next version of this sometime soon. Yeah.
Let's give it for Erica. Thank you for taking